Now, in continuation with the first video where we took an example, we took a problem on non-degenerate perturbation theory, uh, where we assumed a one-dimensional box and and we assigned the perturbation term to the particle in that one-dimensional box. Now let's take another approach. Let's take another problem. Let's consider another classic problem on non-degenerate perturbation theory. Specifically, it leads to what's called as Stark effect. And this Stark effect is observed in hydrogen atom. And here is it where we apply an external electrical field to the system. And so how will we execute this problem is we will try to analyze the hydrogen atom in the presence of weak magnetic field. Weak magnetic field. And the unperturbed system is the hydrogen atom with Hamiltonian H naught. And the perturbation that's inculcated in this system is an electric field. So perturbation is electric field, and let's assume that electric field is E, and this is the perturbation that's introduced to the system. So we have unperturbed Hamiltonian H naught. This is our unperturbed Hamiltonian, and unperturbed Hamiltonian is simply the kinetic energy term, and then we have the potential energy term, and the eigenstates of H naught, they are known from the standard quantum mechanics, and energy levels, the zero order energy levels. What we have, zero order energy levels are this is minus 13.6 electron volts by n scat. And we understand that this n is the principal quantum number, and we know the wave functions and how wave functions are labeled. Now, wave functions, they are labeled like n, l, and m, where this l is our orbital angular momentum and m is our m is its projection, and that may be more precise. This is also called as magnetic quantum number. Now, what we are doing is we are introducing the perturbation. So we are introducing perturbation to our known Hamiltonian as, say, Hp equals E, say, Ez, where this Z is our, in spherical polar coordinates, it's simply r cos theta. That's what we know about it. Now, if I go back to the unperturbed hydrogen atom states, I can write down the unperturbed hydrogen atom states. How we can write them? We have the unperturbed Hamiltonian N, L, and M leading to En naught, N, L, and M. And we have En0 that I have already written, that is En0 is simply minus 13.6 by n square electron volts. Now, for the sake of simplicity, what we will try to do here is we will focus on ground state. The point is to understand the inculcation of perturbation into the system. So the choice that we will choose here is the ground state, and my ground state is simply 1, 0, 0. And this value of 1 is my n, value of 0 is L, value of 0 is M. And we know the wave function for the ground state. So wave function for ground state. Okay, what's that? The wave function for ground state, we know that already, that is psi 1, 0, 0 in terms of spherical polar coordinates. That is 1 by under root of pi a naught cube e to the power of minus r by a. This is our ground state wave function. And this a naught, as all of us know, is Bohr radius. It's Bohr radius. So if I talk about the ground state energy again, that's going to be minus 13.6 electron volts, because for this the value of n is equal to 1. Now let's try to go for the first order correction in energy. So now we want first order correction in energy. So how would we inculcate that thing here? And we have our perturbing Hamiltonian is it is E Z. So how will our we will have the matrix element over here, and the matrix element for E10 will be, it will be 1 0 0, and then EZ, then 1 0 0. All right. So this will be my matrix element for the first order correction to the energy, and for Z, what we have, I'm writing it on the subscript, it is EZ. For Z, what we have is Z is R cos theta. All right. Okay. Fine. Now, so we can write down this matrix element as E1. 1 is, okay, I think E and E will be out. They're both constants, 0 to infinity, then 0 to pi, then 0 to 2 pi, and then we'll have psi 1 0 0 star, r theta and phi, and then what will be left with is r cos theta, and then we will have psi 1 0 0 r theta and phi, and then we will have r square sine theta d phi d theta and dr. So this will be our first order correction, and we have written down the matrix element E. It has to be 1 here. This is the first order correction. E1 1. Now, what is presumably important here is that this wave function, the wave function that we are talking about, psi 1 0 0, it is spherically symmetric. It is spherically symmetric. So if it is spherically symmetric, then the angular part of this integral, will it can be separated out, and the angular integration over cos theta that we have over here is equal to 0. So if we take on this angular part out, so this 0 to pi cos theta, then sine theta and d theta, this is immediately equal to 0. Everybody understands it. And thus, if this part is 0, so everything is 0. So I can say here at this stage that the first order energy correction for the ground state vanishes. So there's no first order correction for the ground state. So order first order energy correction for the ground state vanishes. It simply vanishes. So I will say that E11 is simply 0. So the conclusion is simple, that the first order correction to the energy for the ground state is 0 in this case. Now, if we have to look for its first order correction in terms of the wave function, so first order correction in wave function or state vector. So in order to compute that, we would like to write down the correction to the wave function. So the correction to the wave function is psi n1 is simply sigma m not equal to n. Then we have the matrix element of m, okay, HP, and then we have n. Let's take it this way, divide by En0 minus Em0, and we have psi m over here. Okay, this is already done, this is already defined, and for the ground state, what we have is, for the ground state, so what's our ground state? If I talk about the ground state, I have a situation like this: 1 0 0. We need to basically sum over all excited states, and if for the sake of argument, my excited states like n dash, l dash, and m dash, in all these cases this n dash is greater than 1, so that's going to take me to all the excited states. The matrix element that we have over here, this matrix element is non-zero. Only when the angular quantum number, this matrix element, leads to a non-zero value, only when the quantum number L, only when delta L changes by plus minus 1. I have the value of this correction in terms of the correction to the wave function. So this delta L equals plus minus 1 is the selection rule for basically for the dipole operator. And what's that? That is Z is equal to R cos theta. So I can say here that there's the only non-zero contributions come from the state where L dash, if I choose some L dash, is equal to 1. For simplicity, we will consider only the first case. Okay, the first case will take me to the excited state of 2, and then I'll have L1 and 0. Now the first order wave function, if I had to write for this, so if I write psi 1 1 for this, it will be 2 1 0, and then the perturbation E Z, and then 1 0 and 0. Okay, so divide by E1 0 minus E2 0, and for psi 2 1 and 0. Now let us try to compute this matrix element that's over here, and our matrix element over here is 2 1 0 E Z, then 1 0 0. Okay, what's this? This is simply E and E out, and then 0 to infinity, then 0 to pi, then 0 to 2 pi, and then what we will have here is psi 2 1 0 star. Okay, obviously R theta and phi, and then for Z I will use R cos theta, and then again I will have psi psi 1, then for this is psi star of 2 1 0, and then I will have psi 1 0 and 0, and r theta and phi, then r square, then sine square theta, then d phi and d theta. Okay, so this will be our matrix element. I forgot to write r. The dr has to be here. Okay, so this will be our matrix element for this matrix, in which you have a transition, you have a state, and your system is in an excited state of 2, 1, and 0. Now, what's happening over here is, again, the angular part of this integral can be evaluated using spherical harmonics, and the selection rule ensures, what it ensures is that the integral is non-zero only for this L dash equal to 1. So for other all terms, this whole integral dies out, it freezes out, it goes off, and it doesn't exist. So once this integral is evaluated, we get the first order correction to the wave function, and this is how we attain the first order correction to the problem of hydrogen atom when we subject it to the external electric field, assuming that the magnitude of electric field is on the z direction, and its magnitude is very less. It's weak electric field. So to summarize this lecture, what we have learned is that the first order correction for the ground state of hydrogen in an electric field is 0 for this particular problem. So E11 is 0 for this problem. And what was the next important thing that we understood? That the first order wave function involves a contribution from some excited states, particularly in our case it was 2, 1, and 0, but it requires the detailed calculation of that matrix element, the detailed calculation of this matrix element, where we will not go at this stage, and for those states where this L dash is equal to 1, or this delta L changes by plus minus 1, we have a non-zero value. So the problem that we discussed, what it does basically, it illustrates the non-degenerate perturbation theory that we have applied to the hydrogen atom. And what it does basically, it simply highlights the key steps that we use computing the first order energy correction, which turns out to be 0 in our case, and finding the first order wave function correction. So with this, I would like to say you bye, wish you a good luck, and I hope I could make a difference, and I hope that the students out there around the globe, they should actually involve themselves in solving the problems that look compelling, that look challenging, that look drastic. That's how physics flourishes from theoretical point of view. Okay, bye.